All right, let's dive right into our central mystery for today. How exactly can we extract a true, meaningful signal from a completely chaotic mess of raw observations? If you've ever tracked daily website visitors or looked at a chart of daily stock prices, you already know that raw data is rarely some smooth, easy-to-read line. It's messy. It jumps up and down constantly. So the big question is, how do we find the real story that's hidden underneath all that daily chaos?
Welcome to episode 2 of our Inside Time Series Explainer, where we're tackling the mechanics of moving averages. We're going to look directly at the math, the visual intuition, and the real-world applications of these incredible smoothing tools that are used in everything from financial forecasting to heavy engineering.
Section 1, the problem of noisy data. We're starting off this detective story with a really fundamental challenge. Almost every time series you're ever going to encounter contains random, unpredictable fluctuations. So it basically boils down to this. We have to separate the actual signal, the stuff we really care about, from the distracting noise that's constantly hiding it. You see this everywhere, right? Whether we're looking at daily temperatures, retail sales figures, or stock prices, this signal is the true underlying trend. It's the actual direction the data is moving. The noise, on the other hand, is just those random, chaotic daily fluctuations and errors. Our entire goal in time series analysis is to filter out that noise so we can actually see the signal clearly.
Moving into Section 2, intuition behind the moving average. To actually solve this noise problem, we bring in our primary investigative tool, which relies on a very simple yet incredibly powerful premise.
Let's start with the simple moving average, or SMA. What's really fascinating here is that it treats every single data point in its specific window exactly the same, creating a baseline level of stability. Instead of just looking at today's value in total isolation, an SMA looks at a rolling window of time, let's say the last 10 days, it adds them all up, divides by 10, and uses that average as today's smoothed value. As time moves forward, that window simply slides forward, literally dropping the oldest observation and adding the newest one. To put this into perspective, let's look at an SMA actually in action. See that really jagged, solid black line? That's just raw monthly home energy consumption from 2011 to 2018. The extreme spikes are the noise from seasonal weather changes. Now look at that thick dotted line running right through the middle. That is a seasonal moving average. By averaging the data over a rolling frame, it effectively just wipes out those extreme seasonal spikes to reveal a much clearer slight upward and downward underlying trend in the home's energy use over those 7 years.
But, there's always a trade-off. The SMA is great because it gives us a highly stable trend line since everything gets equal weight. You could step up to a weighted moving average to prioritize specific points, sure, but what if you're in a fast-moving environment like financial markets? You need maximum responsiveness, and that is exactly where the exponential moving average, or EMA, comes in. It reacts incredibly quickly to new information by assigning exponentially decreasing weights to past observations. Basically, the newest data matters most, and the oldest data matters least. All right, Section 3, the mathematics of sliding windows. Let's kind of pull back the curtain on the computation here and see how this builds mathematically without getting immediately lost in complex equations. Let's look at a symmetric linear filter. Take a look at this 5-point moving average of the year 2000 Dow Jones closing values. It's essentially a sliding window where we intentionally drop the extreme ends of the data. For any given point in time, we take the current value, add the 2 previous values, and add the 2 future values, and then just divide by 5. By averaging these adjacent points, we seriously damp down any significant, jarring variations. Notice that the coefficients here are all exactly 1/5. It's a perfect equal-weighted window that just smoothly slides across the data. Now, when we upgrade to the exponential moving average, we don't need those future values anymore, and we introduce something called the alpha parameter. Alpha sits right between 0 and 1, and it dictates exactly how much weight the most recent observation gets. This creates a recursive equation where today's smooth value is a blend of today's actual observation and yesterday's smooth value. This is cool because it allows the model to mathematically remember past random shocks indefinitely, even though their influence fades exponentially over time. And a fun fact, if your alpha is exactly 1, you have absolutely no smoothing at all. You're just looking at your original raw data. Section 4, real-world engineering applications. Let's see how these theoretical sliding windows are actually deployed out in the wild to solve real business problems.
These tools are incredibly versatile. I mean, we're talking about everything from detecting momentum shifts in the stock market to predicting seasonal retail demand. In engineering, they're absolutely crucial for sensor smoothing. Think of a raw radar signal or a manufacturing plant sensor. The raw data is incredibly noisy. Moving averages help operators filter out all that static so they can monitor their systems for genuine anomalies, like a sudden machine error that's disrupting output. But here's the operational dilemma you're definitely going to face. It's basically the Goldilocks principle of choosing your window size. If you use a really short time period, like a 3-month moving average, your model is highly responsive to new data, but it's still vulnerable to getting tricked by noise. On the flip side, if your window size is too large, say a 12-month average, you get this beautiful, stable trend line, but it's going to lag so far behind the actual data that you might completely miss a shifting trend until it's way too late.
Which brings us to section 5, when moving averages fall short. Because as amazing as these tools are for filtering noise, they definitely have a fundamental limitation that we have to talk about.
The crucial thing to understand here is that moving averages, by their very mathematical design, merely smooth out past random errors and transient shocks. Because of this, they completely fail to model long-term dependencies. A moving average model is absolutely perfect for short-lived anomalies, like a manufacturing machine glitch that fades quickly. But what happens if a stock price tends to drift consistently upward after a rise? That is where auto-regression models step in. Auto-regression uses the actual past observations themselves, rather than just the past errors, to capture the real momentum and inertia of the data.
And this leaves us with a really fascinating cliffhanger for our next explainer. We've seen how powerful it is to average the past to find a hidden trend. But what if the data isn't just reacting to random shocks? Instead of just averaging the past, what if the past could actually predict itself? That is the exact mystery we're going to unravel in episode 3, where we step inside the world of auto-regression. I'll see you there.